In today's first challenge question, we are looking at scope, and we're going to be diagramming the implications of global scope versus local scope. The word scope means effectively what are the rules of name resolution. When we refer to x in some function, which x is it in our memory diagram that we're actually referring to? And in this example, we're going to be drawing some close comparisons between these ideas to make sure you understand the implications of the global keyword, which you can see here on line 11, and you first experienced in the most recent project, as well as declaring variables inside of a function, which is what we call local scope, and declaring variables at the global scope. So without further ado, I'm going to turn it over to you to pause the video here and try diagramming this program listing and resume the video once you've completed, and we'll talk through it together. All right, so let's dive into this. So what we've got here are two functions and then some things happening in global. So I'm going to go ahead and set up my stack. So my stack is going to have a globals frame. And in my globals frame, I'm going to have a function f that refers to the definition of f on lines 4 through 7. And all of this is very standard at this point. This is all happening in the heap. I'm going to have a function g that's function on lines 10 through 13. Okay, and then we reach our variable declarations, x and y. So x is initially 0.0 in the globals frame, and y is 0.0 as well. Okay. Then we reach a function call to the function g, right, on line 18. So this is a parameterless function call, or this is a call that has no arguments, calling the parameterless function g. So we go ahead and set up a frame for it. G has a return address of line 18. That's where this call is occurring. And there's no parameters to set up, so we've established this frame. We're ready to jump into G. So we jump in, and right off the bat, we see this special keyword. We see this global Y keyword. Now, in working on the most recent project, you learned that the global keyword means we're not going to have a local variable named Y. We're never going to have something like this in the frame for Y. Whenever we refer to Y within this G function, we're always going to say, oh, there's no Y declared in our frame, so we're going to refer to and mean and imply that we're looking into the globals frame for that particular variable name. So here Y is going to be this global variable, and contrast that with X, which X is being declared as a local variable. All right, so if I wanted to, I could go ahead and carve out some space for X, but we don't know what we're going to initialize X to because we need to complete this function call to F. Okay. So let's do that. Let's check this function call. So f, do we know what f is? Well, there's no function named f defined in G. So we look in globals. Yep, we know that this is the f function up here. We see that it takes a single parameter. We've got a single argument that corresponds. They're the same type. That's great. F returns a float. We're trying to take the result of calling this function and assign it to a float. So the way that we're using it is okay. This is a valid function call. We're ready to go. All right, so we jump in to f, and our return address is going to be line 12, right? So this is where the function call occurred. That's where we're going to come back to with a result, to line 12. And we have a single parameter to set up. It's the x parameter. All right, so x is going to be a variable name that's also local to, or in the local scope of the f function frame that we're setting up. And what are we establishing it to be? We're establishing it to be 3.0, okay? So we've set up our parameters, we've set up our return address, we've set up our frame, we're ready to jump in. And the very first line of this function says, increase the value of x by 1. Well, we've now got 3 x's in memory, right? We've got an x in f, we've got an x in G, and an x in globals. Which one are we talking about? Well, we're talking about the one in our current frame. So remember, with name resolution, the current frame is the lowest frame on the stack that is yet to return. Well, G is yet to return, f is yet to return. We started processing G more recently. It's the last frame that we've processed. We're working on the F frame right now. So this is our local current frame. So the X that we're referring to is this one right here. So X is not going to be 3.0. It's now going to be increased to 4.0, right? And okay, we set up another variable y. Notice we're declaring y locally within this frame. So y is going to be x, which has a current value of 4.0 plus 2.0, so 6.0. And then we reach a return statement. And the return statement on line 7 is take x plus y. So which x are we talking about? We're talking about the local x, which is 4, and y is 6. So that's going to be 10, and return 10. So my return value here is going to be 10.0. Okay, so we're returning y back to line 12. Right, so this is effectively saying, okay, 10.0 is the result here that we're returning back to line 12 where this function call was encountered. And we're taking 10 and assigning it to x, right? So we ask ourselves, what is our current frame once we've returned back to line 12, right? And so this f call evaluates to 10.0. Well, our current frame is this frame, right? It's the lowest frame to not return. F returned. We're done with that frame. We're not going to come back to it. G is not returned. So what we're saying is assign to the x variable that we're declaring here, 10.0. Okay. And we've now completed that line. And then we have this interesting line here, which is assigned to y, which we know is we're going to be reassigning the global y because that's the implication of this. So whatever we return from this function call, which we need to go process, is going to impact the globals frame, but we're not quite there yet. So let's figure out what f of x plus 4.0 evaluates to. So we've already established that f is a function that takes a single parameter of type float. X is of type float. A float plus a float gives us a float. So we know that this is effectively calling f of, and remember our value is 10, so 10 plus 4 is going to be 14. So f of 14 is the next function call we need to evaluate. Now here's something that we haven't really addressed head on before, but you should know that when we call a function for the second time in the same program listing, we set up a brand new frame for it. So let's go ahead and set up another frame like we would any other way. So we've got a second f frame here, right? So there are two calls to the f function in this program listing. There are two separate frames that are individual. And we'll see that there are differences, right? So the return address here is going to be line 13. That's where this call occurred on. So my return address is line 13. And our x parameter is going to be what? Well, it's going to be the argument here, so 14.0. And we're going to say, okay, we've set up our frame. We jump into this function call, and we increase x by 1. So x is no longer going to be 14. And now our current frame is this f frame, right? We're in a lower frame that's yet to return. This is the most recent function call. So 14 increases to 15.0. And then we set up a variable y that is x plus 2. So y in this frame is going to be 17.0. And we return x plus y. 15 plus 17, that's 32. So my return value for this frame for f is 32.0. Right? Now, if we just briefly compare the differences between these two frames, notice that there were significant differences between both of these calls to f, right? So the first call to f occurred on line 12, the second call occurred on line 13. And notice our return addresses are different because the calls came from different places in our program. X and y are different, and the return values are different, right? So to resume back to where we're on line 7, and x plus y was 32.0. And we're returning that back to line 13, which was the call that occurred right here. So 32 is being assigned to y on line 13. Right? So our current frame is the G frame, right? Because now both of these calls to f have returned. So we're back in G and we're working through trying to complete its steps. And we're trying to assign to y. Well, there is no y declared in our G frame. So normally we would say, okay, this seems like we're trying to assign to a variable that we haven't declared yet. That could be problematic. But remember, we said, no, y is, when we refer to y in this function definition, we're referring to the global variable y. So what we're saying is assign, this evaluated to 32.0, right? Because of this return value here. So y in the globals frame is not going to be 0.0. We're reassigning it to 32.0. And we reach the end of this function call frame. We know that there's this implicit return none, so the return value of this call to G is none. And we've completed that. So we jump back to line 18. There's nothing more for us to do here. And finally, we print x comma y. So which x and y are we referring to? Notice we've seen 3 x's in the course of this program and now 2 y's. Well, we're referring to the x and y in the current frame. The current frame is globals. It's the lowest frame on the stack that is yet to return. You know, in globals, we don't really return any value. It's just where the program ends. So our output here is going to be x, which is still 0.0 in globals, because notice in F and in G, we were establishing local variables x. With F, it was a parameter. With G, it was a local variable declaration. So x in the globals frame never changed, but y, because of how we modified it in the G function, y did change. So it was 0.032.0. Oops. Is the result of this print statement, right? And we looked those up from, x came from 0.0 and y came from 32.0. So what is the emphasis of this diagram? The key thing to take home from this diagram is that this global keyword has special implications. As we saw, because in G we declared y to be global, when we assigned to y from inside of that function definition, we were changing the global variable y. Right? We didn't have a y variable in the frame for G. We're saying no, when we refer to y, we're always referring to the global y. For local variables, they can be established in 2 ways. First, if you declare a variable inside of a function definition, and you didn't previously say, hey, this x is a global x, that's one way of having a local variable set up. And so that's what led to, in G, there being this x variable. Additionally, parameters are effectively local variables. And when we set up the frame for these 2 calls to F, notice that we had 2 individual separate x variables. Each could have their own value, separate from the x value in G, separate from the x value in globals. All right. The last thing that's worth pointing out that's new and interesting in this example is notice that in the G function, we called F on line 12 and we called it on line 13. Each individual call to a function is going to result in a new frame for that function call. So if you call the same function twice, you're going to have 2 frames on your stack diagram. Both will have the same name, but they each have their own independent state or local variables. And so, the state of the first call to F, notice we have 12 here, as opposed to 13 for the return address for each of these. And that makes sense because these are 2 different function calls that occurred on different lines of code in our program. So they should have different return addresses. And this diagram allows us to trace through and see that, oh yeah, there were 2 calls that occurred to the F function. They had different parameters that were being passed in. They had different return values. So these are 2 independent function calls. We're going to have 2 independent frames on our stack for them. All right. Next, we're going to take a look at references and lists, but great work on this problem.